Today, I'm going to talk to you about pH and lime rates in container nurseries. This is an issue that, well, I say pH can be an issue I've seen down here around Mobile because we have acidic well water, and in some cases, that's caused some issues. And I've seen it in some other nurseries around the states. Uh, but our topics today we're going to cover is what is pH and why is it important, issues associated with low pH, how does lime work, and some research we did on some different lime rates a couple years ago. And so I'm going to be talking a little bit of chemistry here. And if you're like me, when I was in school, my mind just shut down as soon as the word molecule was spoken. And so bear with me. It's not going to be that complicated. There are going to be some, a little bit of chemistry in here, but don't worry, it's going to be all right. So let's talk about what is pH and why do we care about it? So pH is the measurement of acidity in a solution. And what we're really measuring there is protons or hydrogen. So if you think of acid, think of protons, think of hydrogen. They're all, protons and hydrogen are the same things. And so pH is on a logarithmic scale. So when you're moving between a pH of 5 and 6 or 6 and 7, there's going to be 10 times as many protons or hydrogen in that solution moving down, let's say from 6 to 5 or 5 to 4. pH is important in our containers or in our root zone primarily because of nutrient availability. And so this is the classic, chart you'll see if you've ever had a soil science class looking at nutrient availability, and it's how that correlates to pH. And in some cases, when your pH is too high, nutrients become unavailable. If it gets too low, they may become less available or overly available to the point where you might get a toxicity. I see this a lot with manganese. And let's say if the pH is too high, you might get your iron locked out and might see an iron deficiency. So we're trying to maximize availability of these nutrients. It's different for every plant what is optimum. A lot of the ericaceous plants like azaleas, hollies, loropetalums, they like a lower pH, 4.5 to 5.5. That's what they're adapted to. In most other plants, it's pretty safe to say between 5.5 and 6.5. You get to some of the conifers like junipers and cypress, they like it a little bit higher on that side. But that's why pH is important, because we really want to maximize the availability of nutrients. So let's talk about acids and bases. I've already mentioned that acid is protons or hydrogen. All right, well, a base just accepts that proton. So hydroxide, OH negative, is the base you would most often see. So when we have hydroxide, OH negative, and hydrogen, which is a proton, which is the acid, we put those together, acid and a base equals water, right? So we get H2O. And so these are floating around in solution, constantly going back and forth. Limestone we use as a buffer or as a base in our containers, and that's going to be made out of calcium carbonate, the same stuff Tums for acid indigestion is made out of, right? Well, that calcium, a lot of people think calcium is responsible for adjusting the pH or managing pH in containers. It has very little to do with that. It's the carbonate in that lime. All right, so that carbonate, it can accept one of those protons, so the calcium gets freed off, and that carbonate will attach itself to one of those protons, that hydrogen, and makes bicarbonate. All right, and so that's how we're able to maintain a certain pH in our containers, is we have all this limestone in there, and it's accepting those protons. It's using them or grabbing them so they're not free in solution, causing the pH to go down. So again, neutralization, base and acid equals water. We put these two together, it's going to equal water. So solution equilibrium, that's at pH 7. That's when we have the same amount of hydroxide and the same amount of hydrogen ions in solution. That would be at a pH of 7. Now, this is an example to tell you how much more protons there are than hydroxide ions when the scale gets tipped, when you get below 7. All right, so let's say my well water pH is about 5, and I take 1 drop of that water, which is 1 milliliter, there's going to be over 6 quadrillion protons in that drop of water, but only 6 billion hydroxide ions. So it's out of balance. I'm going to have a lot more hydrogen in there, so it's going to make it acidic. Another important thing to keep in mind, and a lot of people ignore, is alkalinity. This is why it's always good to get a water test for your nursery routinely. Alkalinity is ability of water's ability to neutralize acids. So it's mainly made up of either bicarbonate or carbonate ions. It's not the same as pH. What you're talking about when you're talking about alkalinity is its buffering capacity. All right. So a low alkalinity doesn't have a very high buffering capacity. So you add a little bit of acid, and if it's got a low alkalinity, your pH can drop pretty rapidly, pretty dramatically, because it doesn't have that ability to buffer any changes in pH very well. So a buffer just keeps the pH within a certain range unless it gets overwhelmed. It's also important to know that alkalinity can have a major impact on your container pH. There's some places in the state, they have to actually inject acid into their irrigation water, sulfuric acid in most cases, because their alkalinity is too high. And you keep adding alkalinity through your water, your pH eventually gets too high. In some places, you might have an alkalinity of over 100, and you may not even need any lime in your container substrate mixed in. So, but for us here on the coast, a lot of us have acidic well water. In some places, other parts of the state, where our alkalinity is almost nothing. It's almost like we're using distilled water to water our plants. So we don't have that added benefit of collecting that buffering capacity through alkalinity in our irrigation water. So what lowers container pH? Most everything in nature is trying to lower pH. It's just existing biological activities if everything's going right. And there's some cases where some processes make pH go up. For the most part, in nature, most processes are making the pH go down. In our nurseries, one of the major contributors to this would be low alkalinity and acidic well water. Like I said earlier, we have this in South Alabama and really a lot of places along the coast of Gulf Coast. So you can see here's a well water report from our well here at the station, and you can see we got a pH of about 5. Our alkalinity is 0.3. That's pretty low. You can see there's some sulfur in our water, not a lot. That's kind of an indication that a lot of that acidity came from acid rain. You can see here on the right, this is kind of a map. This is old. I think this may predate the the Clean Air Act, when we were using a lot of sulfur in our coal. But you can see the different pHs of rainwater around the country. And so if you got shallow water wells and you don't have a lot of carbonate or other bases in your soil, and that's the case for here on the coast, we don't have hardly any rocks in our soil other than some iron. That acidic well water is just going to the ground. The acidic rainwater is just going into the ground, and you're going to have acidic well water. Another major impact on acidification would be nitrification. This is a two-step process. This is happening everywhere. It's happening in the water. It's happening in the soil. So this is a two-step process where basically ammonium is converted to nitrite. Then the next step is nitrite to nitrate. All right, so this is a bacterial process where they're converting that ammonia to nitrate. And what happens, if you'll notice, when you got the molecule of ammonia, NH4, and you remember that hydrogen, that proton creates acidity, and you have NO3. So what happens to those hydrogen or those protons? They get kicked out, and that gets put into solution, which also decreases your pH, increasing your acidity. Other things that can create acidic conditions is root exudates. If you're taking in too much positive ions like ammonia and not enough negative ions like nitrate, that plant's got to balance that chemistry, that charge within itself, and so it's going to spit out some hydrogen, some protons to kind of balance things out. So now those protons are in solution, and it's going to lower the pH. And root exudates, iron issues. For some plant species, if they're becoming iron deficient, they will exude hydrogen or protons, and that's purpose is to lower the pH around that root zone to dissolve iron or make it in a more available form for the plant uptake. Another major contributor would be our fertilizer, especially if we're using ammonia. If you're using, as EC goes up, your pH is going to go down. That's primarily through because of nitrification. If you're heavy liquid feeding with ammonia, that's going to drop your pH. It could be your CRF if it failed or you had a massive dump for some reason. A lot of times you're going to see, or most often you're going to see a significant drop in your pH, depending on your buffering capacity, how much lime you have in your mix. If you're not leaching enough and your EC goes up, sometimes I see this in the winter time when people are keeping it a little bit on the dry side, especially under cover, and you'll see where your EC goes up and then your pH can bottom out if you don't have enough lime in your mix. And then if you're using urea, initially can raise the pH a little bit, but it causes an imbalance and also will result in more hydrogen being exudated from the plant roots. So that's why we use limestone. We use lime. It's ground or pulverized calcitic limestone. Most people, though, are using dolomitic limestone. That's going to have a gray color. It contains magnesium. We do that because we think we need a lot of magnesium in our mix, or that's our way we're going to get magnesium. So these particles of limestone, as I already mentioned earlier, is calcium carbonate. That carbonate is going to absorb that hydrogen, all right? And that's going to raise the pH or keep the pH from going down if you look at it like a buffer. So limestone is kind of like a slow release antacid. It's just there hanging out. And as acid comes in from fertilizer or whatever, acid rain or irrigation water, that limestone is slowly getting dissolved and keeping that hydrogen or that acidity from increasing. So this is a great paper from James Altland and Kay Jong. And in this paper, they just basically reviewed all the literature of lime going back a good ways. And one of the interesting things that they point out in this paper is that no matter how much dolomitic lime you add to a mix, you're never going to go over 6.5. Okay. And that's because that lime has to dissolve to become available. And once you get over 6.5 pH, it can't dissolve. So you can put as much as you want in there, and for mostly it's not going to go above 6.5. All right. Just thought that was a pretty interesting statement they made. Like I said, they reviewed a ton of research on lime rates, and most of it recent. And you'll see a lot of variability in here. And one thing that a lot of these researchers kind of fail to do is talk about the alkalinity in their irrigation water. That can have a huge impact on how that lime rate is effective. Some parts of the country, they don't hardly need any lime. Some parts, like here in South Alabama, we need a lot of lime. So the location in the irrigation water is very important when you're looking at lime rates. And so this is the best management practices put out by the Southern Nursery Association a good while ago. This is a 2013 edition. As you know, SNA is no longer around, but you can find this on the HRI website. But in that, the recommendations is for 4 to 6 pounds per cubic yard for most plant species. And I would say on average, at least here in our area, a lot of people are using about 5 pounds per cubic yard of dolomitic lime. And in my opinion, unless you're growing an irrigation crop, then you're going to it's going to be a little low for some things. Especially if you have a problem with your fertilizer, it can drop pretty rapidly at just 5 pounds per cubic yard. So what you'll see often, or what I see, is micronutrient toxicity. If our pH gets too low, you'll have a lot of magnesium available all of a sudden. We use a lot of manganese in our fertilizers or supplement micronutrients because it's not very available at the pH we're trying to grow our plants. But once you drop on down there below 4.5, it becomes highly available and can become toxic. And so it'll show up as an iron chlorosis. So you normally see an iron chlorosis when the pH is too high, so it'll fool you. You're out there thinking, here's an iron chlorosis. All the new growth is get this intervenal chlorosis, but your pH is really low. And you'll do a tissue analysis, and often your iron is sufficient but that's because that manganese is keeping that iron from binding to the chloroplast. It's keeping that iron from doing its job. And so it shows up as manganese, shows up as a iron chlorosis. But there's plenty of iron in the solution and in the tissue. Now, some people will try to spray iron on the plants, but because there may already be plenty of iron in there, it's kind of a useless thing there because that manganese is still a problem. The only solution is to raise your pH and make that manganese less available. So we've been looking at some different things to try to manage pH in some of these acidic conditions, like we have here in South Alabama, looking at different particle sizes. So large particle sizes, that would be screen sizes 8 to 60. The lower the screen size, the larger the particle. So to give you equivalent, that would be like kosher salt, coffee grounds, or grits are kind of within this range. And those particles are about 50% effective. That's because they have a lot less surface area and they dissolve slower. So that 50% effective, that means it reacts fast enough to matter, that 50%. Now, fine particles, that's what we're using when we're using a pulverized, floury dolomitic limestone. You put your hand in it and it feels kind of like flour. That's going to be mostly passing through a number 60 screen or a number 100 screen. It's very fine. It gives you much more surface area to attach those hydrogen ions. It dissolves very fast, and this stuff is, for the most part, 100% effective. Just to give you an idea of the difference in surface area of these particle sizes, if I'm going from a 40 mesh to a 200 mesh, I've got over 3,000 square millimeters. If I'm looking at a whole cubic yard, that's how much surface area I have in a cubic yard, where I have maybe 30 square millimeters if I'm using the 40 mesh. So that's the equivalent of looking at the diameter of Jupiter versus the Earth. It's a huge difference there just because those particle sizes are so small. So we did a little experiment. It was about almost a 90-week experiment looking at Loropetalum and compacta holly. We screened this barn lime, which is just kind of a hodgepodge of calcitic limestone. I don't know if it's stuff they've just swept off the floor of the quarry or what, but it's got all different particle sizes in it. So we screened these to different screen sizes where we had dolomitic, which is, passes through 100. Then we used the 40, 30, and 20 screen sizes. And again, remember, the larger the screen size, the larger the particle. And we also looked at fertilizer rates. We looked at 3, 6, 9, and 12 pounds of lime per cubic yard. And this kind of gives you an example of the different particle sizes here. You can see we have something that is around 60 mesh. Then you have 40 mesh and 30 mesh. And the 40 and 30 are kind of looking like grits, to give you kind of a reference there. I'd say the 30 mesh is more like grits, and the 40 mesh is closer to what a pre-emergent granular would be, that particle size. And so it makes a big difference. This is how those different particle sizes affected the pH over time. You can see the 200 mesh is pretty steep curve there. And then it kind of drops down as the particle sizes get bigger, where you see that 30 and 40 mesh are almost flat, right? And that's kind of interesting to me because I would rather have a kind of a flat curve with my pH over time. But we got to try to get that up to a little bit higher than that 20 mesh is able to provide. And this is kind of how it looks if it wasn't simulated in a model. You can see how the different lime rates with the different particle sizes impacted pH over that 90 weeks. And so you can see lime here. You see the dolomitic lime. This is what we are used to using. So I'm at the 3 and 6 pound rate. And after 16 weeks, now this is with Loropetalum, so it is creating some acidic conditions itself. I'm dropped to almost 4 within 16 weeks. So that 3 and 6 pound rate isn't helping me out a whole lot. Whereas I go up to 12, my starting pH is higher, maybe higher than I want it to be, but I have much longer time within a more acceptable pH range at the higher rates of that dolomitic limestone. Now, what I thought was interesting is when I got to the 40 mesh and the 30 mesh, like I said earlier, you had a flatter curve, especially at the higher rates. And that's kind of what we want to play with in the future here is if we've got these screen sizes, maybe if we increase the rates beyond 12, we can have a higher starting pH and maintain a flatter curve throughout production. And that really depends on the crop and your irrigation water chemistry there. This is just another visual of how this affected pH over time. Everything in red on this little table here is below 4.5. Everything in blue is above 4.5. So you can see we have weeks after planting, and you can see which treatments had the longest maintained pH over 4.5 the longest, and so we have the 12-pound rate and the 9-pound rate at about 42 weeks. At the 40 screen size and 30 screen size, we got up to 56 and 71 weeks with these larger particles. Now, our starting pH was a little bit lower. That's the caveat there. And this is kind of how it shaked out with growth. Now, this is these poor loropetalums were in there for almost 90 weeks. That's a long time to be in a full gallon pot. But you can see the difference in size based on just the rates itself, And also you can see in this picture, we started to get some of that, what I'm calling a manganese toxicity in our lower rates. So this is our 3-pound rates here, getting into our 6-pound rates here. And then we get into our higher rates where we're not seeing that discoloration on the new growth. So in summary, some growers to combat this low, acidic well water conditions, they're mixing ground and pulverized limestone. I've had a hard time finding ground limestone locally. Some folks are using some of that barn lime that they use in barns to kind of sop up animal mess. Some of that is not very available at all because it's such large particle sizes. But if you can find a ground, you might mix it 50-50 with a pulverized. And there is no silver bullet with recommendation. It's going to be really dependent on the location. Acidic well water and non-irrigation crops, you might want to look at lime rates over 8 pounds per cubic yard if you're down in this area. And you need to play around with lime rates because it's going to be different at your nursery, or it's going to be different than what your neighbor's doing. It just depends on your water quality and the fertilizer you're using and a lot of other factors. So what I would recommend, instead of just changing everything over the whole nursery at one time, is to put in a little trial. That's something we can help you with. If you want to do that, you want to look at different lime rates for different crops, give us a call. We'll help you kind of set that up and show you how to do it. And it can really tell you if it's beneficial for you to change your lime rate and what to change it to. Pretty simple to do over a growing season, and that's something we can help you with. But you're never going to know what your pH is if you don't check it. And I know most growers don't have time to do this, doing pour throughs and monitoring your pH and EC, but it's very important, especially if you want to do something like switch to a new fertilizer. We've seen some issues around where people were switching and weren't used to it, and their lime rates weren't cutting the mustard. Their pH bottomed out and they had some issues. So if you want to learn how to check your pH and EC using the pour through procedure, here's a video for you here. We have on the AONLA YouTube channel. You can access it there, and it kind of walks you through the steps and provides some information on some publications where you can read up more on that process. And so that's just a quick and dirty explanation of pH and lime rates. If you have any questions, I'd be glad to take them now.
Are you taking
Jeff,
questions?
like I said, do you have, go ahead.
Are you taking questions in the chat or
I'll take them anywhere.
I have a question.
All right, what's up?
Do you have, us being growers in the Southeast, a kind of a chart of the preferred pH range of the various different things we're growing in nurseries? And as I've seen the problems you went into on loropetalum. But then if you consult research or consult Google, the information's all over the place. Some people recommend lower pedalum at a, near neutral. Some people say that lower pedalum prefer an acidic media, but it seems like in our situation, we might need to aim for neutral, uh, vigorously aim for neutral, given the fact that lower pedalum is going to acidify its own media over time.
Yeah. If you have
That was a
acidic
bunch
soil,
of that was a bunch of questions. I'm
yeah,
sorry.
no, I get it, man. And I don't know of any, good charts with that. And it is, you go and look at the literature on certain crops, and I don't know how much of that is based off of it growing in the soil, which is a completely different animal.
Yes.
I mean, in the soil, on the other end of the soil, you might have aluminum toxicities, which we don't have as much of a problem with, or really have a problem with in our bark media. But things seem to, we have less buffering capacity in that pine bark. So changes have more of effect, and then once you get below 4.5, you can get, hydrogen toxicity, and it can affect your membrane of your roots, So if it's damaging that membrane, it can be more susceptible to diseases, and things like that. But yeah, I feel pretty comfortable going with a higher rate, at least here, with our alkalinity, with lower pedalum. But as far as having a table, with all the different crops, I'm not aware of one. It's a lot of the research that's been done. They don't take into account. I mean, they don't take into account alkalinity. So they may have different lime rates, but it's just specific to that location.
Right.
If that makes sense. But it's something we need to work on.
And it's a hard number to arrive at, because if you like doing a pour through sample, you're measuring the pH in the bulk of the media, but it's very, very difficult to know what is going on in the rhizosphere. The couple millimeters right next to the root that actually is what the plant is dealing with, you may not be accurately measuring.
Yeah, that's right. And there was a recent paper, I believe Jim Owen just published, or maybe did last year, where most of when we're measuring, when we do pour throughs, is more from the bottom of the pot, But yeah, what is actually going on in around those roots? That's a good question. Yeah.
Yeah.
Mhm. Somebody asked, do you have a link for that? Oh yeah, thanks, Ben. Ben posted the link for that container monitoring, nutrition monitoring video. All right. Well, if you don't have any other questions, we'll let loose. I appreciate you guys. Oh, Russell, you got a question?
Well, just while we got this audience on here, I just wanted to quickly remind everybody about the nursery tour that we've got lined up for Charlotte, North Carolina this summer, June 25th through the 27th. So the 25th is a travel day. The 26th, we're going to do bus tours. And then on Friday, the 27th, we got about a half day of some meetings set up. Jeremy's going to present on some research, and we got some labor talks and a few other things, and try to get everybody out by about lunchtime so they can either start their weekend early if they're going to spend it in Charlotte, or get headed home. But if you need more information, shoot me an email or call me. Call the office 334-821-5148. We'd love to have you guys join us. We're going to go to Metrolina Greenhouse, Bartlett Tree Laboratory, and the Daniel Stowe Botanic Garden.
Yeah, it's going to be a great trip. All right. Oh, Stephen, you have a question?
Yeah. For new and upcoming growers, I guess you could say, or people that don't have 30 years experience, or have been in it for a little while. Do you have any type of resources that you recommend to, like, we've tested our water before, but and sent it off, but are there quicker, I guess you could say, like, resources you had to, like, hey, for just a quick test, we recommend this brand? Because I've used 2 or 3 different brands trying to test alkalinity and things with the water, and sometimes they come up, not all the same. And so I just didn't know if there's a resource for, like, hey, this is who we use, this is where we've had success, kind of, that's consistent. So
Yeah. Are you using handheld meters? Is that what you're using, and you get different results?
yeah.
Yeah, you might switch to something that's, like a titration procedure. You can buy little kits with water droplets. And to me, that may be a little more accurate because you're not having to worry about if that sensor's calibrated or, how old it is. But they have little reagent kits, where you look for a color change. And that, to me, that's a little more accurate, and then you can always send it off to, to a lab, and, a lot of times that's what I'm doing. I just kind of routinely. Are you, is, does that answer your question?
Yeah, that does. I mean, we send off every 6 months but we have two different wells. And so
Uh-huh.
sometimes, I'll just like to check it more often to see,
That's,
what
hey,
what's going on. But I've just had, some mixed results, and I thought it would be a little bit more consistent over the course of time, and it is, but for the most part, but one little number, parts per thousand and all that. So I just was like, is that I kind of probably overthink things too much, but
well, that's a, hey man, if you're sending it off twice a year, that's, you're doing a lot more than most people. They might send it off twice in their lifetime. So, uh, that's great.
cool. Thank you.
Yes, sir. All right. Well, if there's no other questions, we'll, let loose, and, thank you guys for joining, and, we'll see you next month.
Thank you, Jeremy.
Thanks.